Okay, for this FRQ we have the shaded region R. It says that we're in the first quadrant bounded by the graph of 2 square root x, the horizontal line y equals 6, and the y-axis, and here's your diagram. For part A, find the area of R. Okay, to find the area, we're going to integrate. You can see that the region exists from 0 to 9 in the x direction, so we're going to integrate from 0 to 9, and then when we integrate, it's going to be the top minus the bottom, and that will give us the area of the shaded region. So our top is y equals 6, our bottom is that curve 2 square root of x. So let's get that set up. Alright, so here's our integral. We have 0 to 9, and then we're integrating 6 minus 2 square root x dx. So first I rewrote that square root x as x to the 1/2, and then now we can go ahead and integrate. Right here we're going to add 1 to this exponent, so you get 3/2. Drop this 2 down, and we divide by this new exponent, which is the same as multiplying by 2 over 3. And our last step is plug in 9 minus plugging in 0. And to evaluate this, we're going to do the root first. The square root of 9 is 3, and then 3 cubed is 27. And your final answer is 18. Part B says write, but don't evaluate, an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 7. So the thing to note about this is you have your shaded region, your axis of rotation is y equals 7. There's a gap in between, so therefore this will require the washer method. We're rotating around a horizontal line, so this is a dx problem. Capital R goes from the axis of rotation towards the shaded region, but it goes to the further part of the shaded region. Lowercase r also towards the shaded region, but you go to the closer part of the shaded region. Since this is a dx problem, we want our expressions over here to be written as y with respect to x. First, note that capital R corresponds to the square root graph. So I wrote that right here, y equals, and then you have 2 square root x, so we have y in terms of x. For lowercase r, no matter where you draw it, it's always a constant value of 1. And finally for capital R, to finish our expression, we're going to think of it as top minus bottom. So the top would be the value 7 minus the bottom is that square root curve that we just identified right here. So again, when you're writing your expression for capital R, think of it as top minus bottom. Okay, I got these labeled, so this is a dx problem in the x direction. Look at your shaded region, and your shaded region exists from 0 all the way to 9, so that's going to be our limits. And for a washer method, the integrand is capital R squared minus lowercase r squared. So we take these expressions and plug them in for capital R squared minus and lowercase r squared. So here's our setup. For part C, it says region R is the base of a solid. For each y, where y is between 0 and 6, the cross-section of the solid taken perpendicular to the y-axis is a rectangle whose height is 3 times the length of its base in region R. Write, but don't evaluate, an integral expression that gives the volume of the solid. So since we're perpendicular to the y-axis, it's going to be a dy problem. So your setup for a volume of known cross-section is noting that it's dy. You're integrating for the shaded region from 0 to 6. A of y dy will be our formula, where A represents the area of the cross-section. It says that the cross-section is going to be a rectangle. It says the height is 3 times the length of the base in region R. So this is going to be the base, and it's telling us the height of the rectangle is 3 times this. Okay, so the height of the rectangle is this segment, and we're labeling that x because it starts on the y-axis and it goes a generic distance horizontally out to the curve. The base is 3 times x. So now if we wanted to write the area of the rectangle, we would take this x and times by 3x to get 3x squared. However, it's a dy problem, so we need to get this with respect to y. So if you take the equation y equals 2 square root of x, we can solve for x. So first you get y over 2 equals square root of x. Go ahead and square both sides. So we get that x equals y squared over 4. So this expression represents the height of the rectangle. Since the base is 3x, I took this expression, plugged it in for x, so you end up getting 3/4 y squared for the base. And to get the area of a rectangle, you would multiply that height and base together. So here's the height, here's the base. And finally, for your volume of known cross-section, you have the integral from 0 to 6 of 3/16 y to the 4th dy.